So in gas chromatography, you have separation based primarily on boiling points. And the problem with this is that for a given temperature of the column oven, if you hold that constant over a range of time, you'll get compounds with very low boiling points eluting very, very closely together, and compounds with high boiling points taking a very long time to come off. This leads to a general elution problem, which says that we cannot have both adequate separation of a range of boiling points and get them off in a reasonable runtime. So this obviously presents a major setback in chromatography. However, there's a correction that we can do, and that is called temperature programming. So in the case here that I've shown, where we have a single temperature constant over time, this is called an isothermal separation. Iso meaning same, thermal meaning temperature. It's at the same temperature. So when we instead are going to do something called temperature programming, okay, what does this look like on a temperature versus time scale? Okay, so our temperature program basically says this. Let's start off with a very low temperature, lower than what we were using in the isothermal. Okay, what does this do to our separation? If we have a very low temperature, we're going to get much better separation between our low boiling point analytes. Okay, it's going to take them a little bit longer to come off, but we're going to maximize our ability to separate those early ones. And then in the middle here, we know that those were reasonably separated, so we might want to pick up the temperature here at a rate that's going to get these to elute still with good resolution. So our next three components will also come off with good resolution. Okay, they might look something like that. Now, to get these last few off, we want them to come off in a relatively quick manner. So we'd want to be at a nice high temperature, higher than we were with that isothermal rate, or isothermal separation. Okay, so we can finish it off at a high temperature. And what we find is that our end compounds, because we're at a higher temperature, are going to elute sooner than they would with the isothermal one. So we may not need the entire time. So these might come off like this. Okay, and now we've cut the amount of time that it takes off from our separation. So a temperature program, as opposed to isothermal, has a couple of advantages. Okay, we're ultimately driving the equilibrium to go or to the gas phase for these large compounds that get them to elute earlier. While at the low temperature, we're driving that equilibrium to the stationary phase to actually get good separation of the early components. So we're getting both the separation of low boiling point components and getting high boiling point components to exit the column in a reasonable amount of time. So what does this ultimately lead to? Well, temperature programming ultimately leads to a couple of things. It leads to, first, narrower peaks. And why narrower peaks? Okay, if we remember in the Van Deemter equation, the longer analytes spend in the column, the more time there is for diffusion. So we get a lower term B if we're going to be able to get them off the column much faster. In addition, we get a lower CS term because we're having more control over those end peaks interaction with the stationary phase. Ultimately, this is going to lead to improved resolution. Now, the second perk that we get here is, again, better separation of lowering boiling point compounds. And as we said earlier, this is because we get to start at a low temperature, lower than what we would be feasible to work with at an isothermal separation. Low boiling point compounds. And at the same time, we get ultimately faster separations because we don't have to wait as long for those end compounds to come off the column, because we end up at the end at a higher temperature. Now, as I've shown this here, we have a single step, and we would call this the ramp. And this would have a specific rate of a number of degrees over time. The exact ramp amount, how many degrees over what given time, can vary from separation to separation. And you can control that by controlling the oven temperature. Now, another thing we can control is how many ramps. Let's say we want to do a temperature program. We could start at a low temperature, ramp up somewhat, and then hold at a single temperature for a little bit of isothermal time, and then do a second ramp or a third ramp. Okay? We can use multiple ramps to optimize our separation depending on the boiling point and points of our analytes. Okay? Something that you always need to check, though, is the maximum temperature listed on the column. If your end temperature is above the max or even close to the maximum temperature for the column, you get something called column bleed. And this is when the stationary phase actually starts to thermally decompose, and you end up with the stationary phase volatilizing and exiting the column along with the mobile phase. So what are some signs of column degradation? You're looking for a high baseline on your signal. You can also see the peaks broadening, or you can get a peak tailing, where you have a peak that is not a Gaussian shape. You may also have a shift in retention times because your analytes are not interacting with as much stationary phase, because some of your stationary phase has been removed from the column due to this column bleed. So those are all aspects to the general elution problem, and how we go about correcting it using a temperature program for our oven temperature control.